Hello everyone, my name is Rez Mani and I'm an application scientist with the company ASP Laser Inc. And today's webinar is called Laser Cleaning Method and Case Studies. Thanks very much for joining us today. We are doing this webinar. Actually, I would like to ask to put your microphones on mute, please, if you don't mind. Like I can see there's some background noise. Yes, yes, everything is good. Yes, thank you so much. So we haven't been doing these webinars for a while. Our company was going through some restructuring. It used to be called Allied Scientific Pro. Now we are called ASP Laser Inc. So we are starting this webinar after a few months delay. This is our first webinar after the break. And this webinar is being recorded. The recording will be sent to you. So you will receive it, and we'll also send you the links for all the videos that we show, because the GoToMeeting platform is not really meant to show videos, but I'm going to show some videos anyway. So if you want to look at these YouTube videos again and hear the sound properly, you can watch them. If you have any questions, my email is written here. Feel free to email me after discussing your specific case of laser cleaning, and I'll be glad to answer it. We also have a Q&A session at the end. You can ask your questions at the end. So let's look at the outline of the talk. We will start with introduction to laser ablation, which is a more general case. So when we talk about laser ablation, we could think of drilling, scribing, cutting, and cleaning, and so on. And then we would look at different types of lasers that are used in laser ablation. And then we go to laser cleaning, which is a subset of laser ablation. So laser ablation has many applications, and laser cleaning is a subset of that general case. And we will compare with other competing surface cleaning methods. We talk about advantage of laser cleaning compared to other methods, and what are the accessories that were designed to mitigate disadvantages of laser cleaning. Then we go into physics of laser cleaning and look at dependence of laser ablation on material properties and laser parameters. And then we have two different terms here. The applications. Whenever I talk about applications, it means that, I found this application from some source. We haven't done it ourselves, but this application of laser cleaning exists. And then we also have case studies. These are the projects that we have done ourselves. So application, we just found it. We know it exists. Case study, we have done ourselves. And then we introduce, before the case studies, I would introduce the several laser cleaning systems that we offer: 100 watt, 200 watt, 300 watt, and 500 watt. And then we would end with some conclusions. So if we look at the principle of laser ablation, which is the more general case, we would basically see that the laser beam is focused on the surface, and focusing that on the surface would create high temperature, and these are usually pulse lasers that are used. So the high temperature would create high temperature gradient and a mechanical stress, high mechanical stress, and plasma formation, and a shock wave. And this shock wave will blast the surface and cause the mechanical breakdown of the surface. So this is just basically the principle of laser cleaning. So actually both CW or continuous wave lasers and pulse lasers could be used, but we'll focus our attention on pulse lasers because there's more control on the parameters of the laser, such as pulse duration and repetition rate, and all of these will affect the laser cleaning process, which I'll discuss later. So for the laser cleaning mechanism, I'm showing this example from a Malaysian author in car industry. Here you can see that there is car paint. I'm going to just activate the laser pointer here. So the car paint is on a metal substrate and usually it consists of resins, pigments, solvents, and additives. And the laser beam is shining on the coating and it gets absorbed by the coating. And then basically this plasma is formed, shock wave causes the mechanical breakdown of the surface and the coating is removed. So this is the basic mechanism there. I should mention that in this particular case, the coating actually absorbs the laser radiation, but there are other cases where the coating is transparent to the laser radiation, and the laser radiation is absorbed by the metal substrate instead. So that is called spallation, which we'll get to when we're talking about the nuclear industry cleaning. So moving on, uh, at lower energies, you can also remove the coatings using evaporation, causing flame and smoke. So it doesn't always have to be through a shock wave. So, but normally, plasma is observed. Even in all of the videos that we show, you see a plasma is formed, is glowing, and causing the mechanical breakdown of the surface. But you can also have evaporation method. So this is a number of lasers that are used for laser ablation, which is a general case. I'm not going to go too much into detail in this because we just want to have a quick idea what type of lasers are there. So you have a solid state lasers, which are here. You can see the neodymium YAG laser at 1064 nanometer, and also the titanium sapphire laser, which emits between 650 to 1100 nanometer. These have a crystal, and they emit in near infrared. They are used for cleaning and ablation. And then you have gas lasers. So in the ultraviolet, you have the excimer laser, which is more for lab purposes. It's basically not fit for a field use. It's more like a lab use. It's a low rep rate. It's used for germicidal applications and photolithography. So there's the excimer gas in this. And then you have the CO2 laser at 10 micron, which is heavily used in industry for cutting applications, also for cleaning. And that operates at 10.6 micron. However, the most popular laser that basically we use in the laser cleaning is the fiber laser. And our systems are also based on fiber laser. So in case of fiber lasers, instead of having a mirror, there is scribing in the core, as you can see here on the right side. So this would act as a mirror kind of, so it reflects a particular wavelength. It's designed to reflect a particular wavelength. So if you pump the fiber laser with diode laser, and this fiber material is doped with ytterbium, erbium, or thulium, some rare earth elements. So the laser beam is generated inside the fiber and gets reflected from this fiber, this grating scribing inside the fiber and exits the fiber. So this would give the great advantage of flexibility for the fiber laser so that you can take it anywhere and bend it, and if you need to get to a hard to reach place in a ship or something, you can always bend the fiber and go there and clean it. And this has other advantages as well, such as near IR, such as high pulse energy, high average power, good beam quality, variable pulse length, and the most important uh, advantage is the flexibility of reaching hard to reach places or surfaces. Okay, so now we look at laser cleaning as a specific case or a subset of laser ablation, and basically it removes unwanted layers or contamination from solid substrates. And here is a picture of our first laser cleaner that was designed a few years ago, maybe about 5, 6 years ago. This is a 100-watt system, and you can see this is the pumping mechanism in this box, and there's a fiber optic, an isolator, and then there is a laser head which contains the galvos and the lens. The lens, there are three different lenses, I think 15 centimeters, 20 centimeters, and maybe 50 centimeters, so different focal length lens. So let's take a look at a video here to see how it works. So I'm gonna just remove the laser pointer. Just a minute. I'm going to have to remove the laser pointer. Yes. So you can see the laser cleaner is cleaning the industrial primer on a structural steel. And this is the plasma that is formed. It's lined. And all the debris are being collected by this vacuum tube. So it's a dry process. Everything is being collected by the vacuum tube. Okay, so that's a demonstration of our laser cleaning system, the 100-watt. So which applications does laser cleaning have and in which industry? So first of all, you can say in the bridge, in the restoration and conservation industry. So, for example, the Canadian Parliament building was cleaned. Here you can see it has a lot of pollution and dirt on it. This was cleaned by a laser cleaner. You can also clean bridges. We have cleaned some bridges in the Quebec areas from rust mainly. In the aerospace industry, we did a demo for Canadian Aviation Museum. I'll have a video for you later. Ship's body parts. We went to Irving shipyard. We cleaned the ship with the laser, parts of the ship, the body of the ship, and some tools. And in the industrial section, we actually did go to a Caterpillar plant and cleaned some of their Caterpillars. Our laser head is mounted on a robot here. We also have been to some radioactive, can say, facility, treatment facility, and cleaned some parts there. I'll have a video of that as well. So what are the important parameters of laser cleaner? Number one is wavelengths. So you have to take into account that some wavelengths are heavily absorbed by some material, and some are basically reflected. They're not heavily absorbed. So for example, if you look at the mid-infrared laser light, it is heavily absorbed by paint, but metals reflect most of the mid-IR. So if you have paint on a metal, the paint will absorb the mid-IR and the substrate will reflect it. So it's inherently safe to use the mid-IR to remove paint from a metal surface. But the problem is that mid-IR lasers are not compatible with fiber optics. So you can also achieve the same result if you tune properly with the near IR. So I'll talk about the parameter tuning later. You have the pulse width. So increasing the pulse width would increase the depth of ablation. So it will go deeper. If you have you're concerned about the substrate, and you have a very thin layer of a coating, you should not use a big pulse width because it will cut into the substrate. It could damage the substrate. Pulse energy, the stronger the pulse, the higher is the rate of ablation. There's more energy. Beam shape, if you are cleaning something that has lots of nooks and crannies, or a concrete block that has a lot of small pores, then you need to use a smaller beam so you could clean inside the pores. But if you're cleaning a wall that has no features, you could use a 20 centimeter long line to clean faster. And then repetition rate, higher repetition rate, if we keep the pulse energy constant, would um, increase the depth of ablation because of the heating accumulation effect that exists. So the threshold fluence due to heat accumulation would be reduced. However, in our systems, whenever you increase the pulse rep rate, you also reduce the pulse energy. It's very hard to keep the pulse energy the same and increase uh, the pulse rep rate. So there are some parameters to play with, basically. But if you could keep the pulse energy the same, increasing the rep rate will reduce the threshold ablation uh, or ablation threshold. Now, there are other competing methods of cleaning surfaces. I'm sure you're familiar with some of these methods. So mechanical abrasives here on the left, this could potentially scratch the surface. And chemicals, when you apply a chemical and wait for a period of time and then scratch it. So this could damage the substrate, and it's a slow process. And then you have these other methods which high pressure nozzle basically sends out some secondary medium into the object, like sandblasting, water jetting, and dry ice. And in fact, there's a recoil here. The operator needs to hold the gun really tight, because the recoil produces this backward force. So they also need to wear heavy personal protection equipment, because the sand or the water or dry ice could bounce back and hit them. Also, the other problem with these nozzle methods is that all the contamination will get into the environment, could potentially go into power into water supplies, and especially if it's radioactive, is even worse. So it's not a clean. It makes the environment dirty, basically, by spreading the contaminant. So use of a secondary medium here also would add to the cost. So that's a concern for these competing methods. However, for the laser cleaning, this table shows that it has many advantages. I'm not going to go through each one of these items, but when we send you the recording of the video, you could look through it and compare laser cleaning with other competing methods. Now, what about advantages of laser cleaning? So it's non-contact. There's no secondary medium. So it's only photons that are hitting the surface. Low environmental impact, because all the debris is being collected on the spot. It's a dry process. And then you have selectivity, localized action, versatility, and controlled removal. So in order to show this, like for selectivity, there's a video that I want to show where the laser beam is cleaning the Coke Zero can. So this is a very good indication of what selectivity means. So let's look at this video together. So here you can see the laser beam is shining on the Coke Zero can, and it is only removing the black paint, although it is shining on the red and white as well. So why is that? It's because the threshold ablation energy, or ablation threshold energy, of the black paint is lower than red and white. Because it's black, it absorbs more, so less energy is needed. So if you tune the energy of the pulse so that it is above that threshold energy for black, but below red and white, it will only remove the black, even if it is shining on the red and white. And this is something that is unique to laser cleaner. If you cannot achieve this with, for example, sandblasting, because sandblaster would remove everything. So this is a very good demonstration of the versatility of laser cleaning. So no technique is perfect. So obviously the laser cleaning will also have some disadvantages. And what are those disadvantages? One is the need for focusing. So if you remember when I was showing the 100-watt system, there was the lens part in the laser head. So you need to keep that lens at the focal distance from the object you're cleaning, not at any distance. With a sandblasting nozzle, you could keep it at any distance, but for this one, you need to be at the focal distance so that you hit the focal, you can basically illuminate the object from the focal distance. And you at that point, you hear maximum sound emitting from the object, and also there will be maximum amount of light that is emitted. And then you know you are at the focus. So this is something that is, you can say, disadvantages compared to the other methods that don't need this. And then as far as the speed is concerned, if you only compare the speed of laser cleaner with, let's say, sandblaster, it will take longer. But for sandblasting, you need to prepare the medium beforehand, and then you need to clean up after. So if you add up those times, then the speeds are comparable. So in order to mitigate some of the disadvantages that I listed, we have designed certain accessories. So one of them is this accessory on the left side is called the fume extractor nozzle. So it has wheels on one side, and there's an opening on the left side where you can insert the laser head. So once you roll the wheels on the surface, it will keep the laser head at the focal point, and it will clean. You don't need to worry about holding it at the focal point. You can also put the vacuum pump attached to this. Will take out all the debris. The other, you can say, accessory is the robotics. And here is a video that shows the robotics. Just bear with me for removing this.
Students in low-income communities and their education is growing.
Advertisement. Sorry about that. Yes. Yeah, here is a robotic cleaning of a pipe from the rust. So you can see that the robot is holding the laser head, the 100-watt laser head at the focal distance, so it's not moving. Okay, moving on, we would go to another accessory that has been recently designed and used. So it's called the magnetic box, or magnetic enclosure for laser fume capture. So this box has some windows, transparent windows, and on one side you can attach the nozzle for the vacuum pump. So you can attach it magnetically to any metal surface, and then you can shine the laser through the glass. So it would remove the paint or the contaminant rust, and all the debris is captured inside the box and removed by the vacuum pump. So it's pretty convenient to use this magnetic box. We also have the Cobot RAS program, so collaborative robotics as a service, which we, basically lease for these rates, and they are basically, you have Tom, Jane, and Rudy, and they're capable of carrying different amount of loads. So Tom is 3 kilograms, Jane is 5 kilograms, and Rudy is 10 kilograms. And they have different application programmings, and they're quite useful in helping for laser cleaning. I'll show you a video of using one of those when in one of the case studies. All right, so let's go into a little bit of a physics of laser cleaning, try to understand the physics of laser cleaning. So let's look at this diagram. So you see this beam of light is shining on this block, and it is the optical beam is penetrating through the depth of L alpha. This is the optical penetration depth. So uh, if the pulses are less than 10 picosecond, the optical penetration depth is the same as thermal penetration depth. So there's no heat outside of this L alpha. But if the pulses are greater than 10 picoseconds, the thermal penetration depth is greater than L alpha. So the yellow demonstrates the thermal penetration depth, and the orange represents the optical penetration depth. So some important material properties that are concerned here is optical attenuation coefficient, thermal diffusivity, heat of vaporization, and important laser parameters could be pulse width, fluence, beam size, and wavelength, basically. So in case of the thermal penetration depths, the the penetration depth depends on the product of diffusivity and the pulse duration, square root of that, of course. So there's a square root of pulse duration dependence, which means that the longer is the pulse duration, the bigger is the thermal penetration depth. And therefore you need uh, basically more energy to remove the material. To achieve ablation, enough energy has to be deposited per unit area to ablate the material, and we call this the threshold fluence. So this threshold fluence, which is the energy to remove the energy per unit area to remove the material, for short pulses less than 10 picosecond, is independent of the pulse width. So threshold is density, heat of vaporization, and basically optical penetration depth. But in case of pulses that are greater than 10 picosecond, this is dependent on L tau, which is the thermal penetration depth, and that depends on the pulse width. So threshold fluence increases with increasing pulse duration. So here's a difference between the two cases that we have to consider. Also, there is the long and short wavelength behavior. We talked about this a little bit at the beginning. So, for example, for metals, you can see at long wavelengths, mid-IR wavelengths, the absorption coefficient is very small. But say for aluminum, near IR becomes larger. For dielectric material like plastic, ceramic, and glass, the absorption coefficient is very high at 10 micron, but it gets very small at near IR. So these are some of the things that one has to consider when you're cleaning, at what are the absorption coefficient of one material on what substrate. So here we get to some of the applications. Again, we haven't done these ourselves, but this can be done. So here you see a hangar where this uh, airplane is being cleaned by several robots. Probably these are CO2 lasers. You cannot see any fiber here, but the robots are cleaning different parts of the aircraft. And why do we need to remove the paint from the aircraft? Well, first of all, the paint gets old and gets damaged with time. And secondly, you can't paint over the old paint because you need to remove it. Otherwise, it would add weight to the aircraft. So that's the reason that you need to remove the old paint before putting a new fresh layer of new paint. And using lasers are a very good way of doing that. And if you use a near IR laser, you can adjust the parameters to make sure that it doesn't damage the substrate and clean very effectively. Another very interesting application is the laser cleaning for nuclear decontamination. So here in Canada, in provinces of Ontario and Quebec, we don't use uh, we don't use coal for generating electricity. We use 60% nuclear energy for generating electricity in Ontario, and Quebec has a lot of water, so 94% of the electricity is generated using hydroelectric. So we depend on nuclear energy a lot here in Ontario, for example. But the problem is that every 30 to 40 years, these nuclear reactors, they develop a crack in their structure and they need to be dismantled. So because the walls are radioactive and the tools inside are radioactive, they need to be cleaned. You just cannot just throw them out. And normally the cobalt 60 is deposited on the feeder pipes. So what happens is the corrosion of the metal pipes causes this product to be released into the reactor coolant, and it will go into the is transported into the active area, gets radioactive, and then comes back and deposits on the heat transport pipes and tubes in the form of oxides. So if you want to clean uh, the metals or the tools, you need to you need to remove these oxides. And these oxides are actually transparent to near IR laser. If you want to clean them with the near IR laser, it would basically get absorbed by the metal underneath, and then the shock wave would blast the oxide. And this process is called spallation, which we talked about when we were talking about the car industry. So this would work very well for nuclear industry. We have done some measurements or some cleaning in Canadian National Lab, which is our nuclear center here in Canada. So let's look at some of our laser cleaning system. I already showed you the 100-watt system. This was the initial design that we had, this box with the laser head and the fiber. And then a while ago, a few years after that, we designed a 200-watt system, which is narrower and longer. It also has some cabinets for storing basically goggles and different lenses and so on. And there's of course variability in the repetition rate and pulse width, and this has longer fibers as well. And here is the Gen 2, 100-watt Gen 2, because there was a need in the industry for having a portable laser cleaner that one can carry like a suitcase. So we came up with this design, which is 60% smaller and 40% lighter. And currently, this is the only 100-watt laser that we offer. We don't do the old style anymore. So this one also, instead of iPad, the other one has an iPad for control. This has an enhanced user-friendly interface touch encoder, which is used there. And this has been used in several trials, and especially for ships. If you want to go into the hatches and there's a limited space, a single worker could carry this like a suitcase and do the cleaning. We also have a 300-watt system that has been designed that looks like this. And there is also the 500-watt, which is the highest power we can offer. And this has basically a lid where you can coil the fiber, which is 11 meter or 22 meter, and keep it safe under the lid. It also comes with a chiller, so you need to cool the laser head. This is a chiller 15-meter main power cord to chiller system, 5-meter water cooling hoses, and so on. So now we have time to look at the case studies. We already talked about the principles of laser cleaning and the system that we had. So now we can just look at the case studies. That's the interesting part. So the first case study was done back in 2017, testing at the Perma-Fix Nuclear Decontamination Facility, which is in Richland, Washington, and they deal with intermediate and low-level radioactive contamination, and they clean them. So we took our old style 100-watt system there, and they defined in certain area under negative pressure. So the actual box was sitting outside of that area, but the fiber optic and laser head were routed in, and you can see their engineers and the radiation engineers on working on different metal pipes, metal surfaces, and things like that. They're cleaning them. So several different objects were treated: concrete ecology block, metal jackhammer, metal C-clamp, and so on. And for some of these objects, several scans were required to clean them. So here you can say, or rather passes, I shouldn't say scans, several passes were required to clean them to bring them below 1,000 disintegration per minute, which was defined as the clean level. So let's look at the video from this trial. Bearing with me for removing this advertisement.
On every vacation at a verbal home, there's someone like you who reunited the.
So here the metal is being cleaned, the metal plate. The engineer technician is cleaning it with our laser cleaner 100-watt system, and the radiation technician is measuring the disintegration per minute. And this tube goes to the vacuum pump through the HEPA filter, so collects all the debris. You can see that the laser head is all wrapped in plastic bags so that it doesn't get contaminated. Here there's a C-clamp that is being cleaned. It's radioactive, so after 2 passes with laser, it went down to less than 1,000. Initially it was 5,000. Here you can see the body of the C-clamp is being cleaned. There is a curvature there. And here is a torch head is being cleaned. It was 15,000 before, and after 2 passes was 4,000. And finally, there's a concrete block, which was the most difficult one. That's why it has a small beam, because there's kinds of pore structure. So it has all kinds of porous structure, which makes it more difficult to clean. Okay, so this was the demonstration at Perma-Fix. And here's the second case study, radioactive robotic laser cleaning at McMaster University's particle accelerator, the contamination facility. So we wanted to test the laser cleaning with radioactive material, where we also use cobots to hold the laser head. So we went there to McMaster University in Hamilton, Ontario, and they have the accelerator facility there. They could generate this radioactive isotope F18, that is a short-lived isotope. Its half-life is only 109 minutes. So basically, if you wait one day, all of it will disintegrate. So it will not be radioactive anymore. And this was only done for safety reason. So they have a hot cell in this area. You can see the windows in this area, which the door, the lid could be removed. And so we placed the metal objects inside, and then we used the laser cleaner to clean those objects. So here you can see how we mounted the cobot that is holding the laser head, and it is cleaning uh, different metals. So 5 different metals were used, including aluminum uh, and chrome, vanadium, stainless steel, brass, and steel. Some of these metals were hard metals, and some of them were soft metals. So, for example, brass and aluminum are considered soft metals, and the other ones are hard metals. So, normally, this were contaminated with about 5,000 to 10,000 counts of radiation. So the F18 was dissolved in a methanol solution and then applied with a paintbrush on the surfaces. And then the radiation engineer measured the initial contamination. And then after several passes, we measured the contamination. If it was below 500 counts per minute, then we declared it as clean. So normally for the hard metals, we use an aggressive setting of 350 nanosecond pulse duration, so longer pulse duration, and also for the soft metals we use 200, so less aggressive. So 120 kilohertz was normally our repetition rate, but in some cases we had to decrease it or increase it depending on how the cleaning was going. So here's a video that shows how the cleaning was done. So this camera was installed inside the hot cell, and it shows the whole laser cleaning process. So I'm going to run this. So here you can see it is the radiation engineer is measuring the contamination before the cleaning from this brass plate. And here's the laser head that is mounted here, is held by the cobot. And then at this moment, the laser head starts to do its scan. It's already programmed. So it's going to move across and clean the surface through several passes. So we'll go and come back. And then you would get the radiation engineer would measure after. And if it was below 500 counts per minute, he would stop the process. If not, we would continue on. So these are the results that we got. So you can see for stainless steel, chrome vanadium, we use 350 nanosecond, and for aluminum, we use 200. For brass, we should have used 200, but for whatever reason, we used 350. If we were going back there, we would have used 200 nanosecond for brass as well, because it's also a soft metal. So you can see there's less number of passes required for aluminum and brass as compared to the hard metals because it's more difficult to remove the contamination from them. Also, you can see for the last one, from 5 to 10 passes, we only got 200 counts per minute decrease. So we had to change the setting to something more aggressive. So we reduced the pulse repetition rate to 80 kilohertz because there will be more dwell time. So that's a more aggressive setting. And also the scan, the 80 is not because of the dwell time. The 80 kilohertz was used because we would increase the energy per pulse. And this one, the scan speed was reduced from 6,000 to 3,000. So slower speed has a bigger dwell time on the surface. So after we made these changes, the next 5 passes dropped the contamination from 800 to 500. So it worked, and then we stopped at that point. So it was a very successful operation. And then the third case study was for laser cleaning in ship industry in the Irving shipyards in Halifax and Shelburne. And I read an article that uh, the shipping industry has $1 billion rust problem. So laser cleaning could be very useful in cleaning this rust. So here is the shipyard, and you can see the ship already was wrapped in tarps because they wanted to do sandblasting, so they didn't want the contamination to get into the marine environment. So we took all our lasers, 100 watt, 200 watt, and 500 watts there. They're all in these boxes, and we did onshore and offshore cleaning. The first cleaning was done on the plenum, so the 500-watt laser was kept on the deck, and then the 15-meter fiber cable was routed inside the plenum. And plenum is actually responsible for circulation, for heating and air conditioning in the ship. So if you look at the picture of the ship, this area is the plenum, and this is where what was being cleaned. So they wanted us to not only remove the paint, but also make a 4 mil average profile with the laser cleaner. So we did that using the 500-watt laser successfully. Then I also wanted to clean the bilge, but because you had to go through hatches, the only system that could go down there was 100-watt, and this was the old style 100-watt system. It would have been easier to use the new generation 2 version. It would have been easier. But anyway, this was lowered and it cleaned the rust and paint from the bilge. A 200-watt laser was used in the onshore cleaning facility in the Halifax shipyard and cleaned pipe flanges, pipes, bike frames, welded planes. And in Shelburne ship repair, which is also onshore, several objects were cleaned, rust on the flat surface of steel substrate, uh, and intersleek paint over steel substrate. So after all these operations, we got some feedback from the uh, uh, share, basically Irving staff, that this is all very good, but it would be nice to reduce the size of the laser head and the laser controller, which we have done in generation 2. And also it would be nice to extend the fiber optic cord, so make it longer. So these are some new design ideas that we got as a feedback from Irving. Here's case study number 4, leaded paint cleaning. So as you know, lead is very toxic, And cleaning laser with laser cleaner, cleaning lead with laser cleaner, one has to be very careful. It's not only important to use HEPA filter, but you also need to use BULFA filter that has these scroll plates. So basically, the heavy particles that are ablated enter this, and they are taken away by these scrolls due to centripetal force. They drop into the compartments, and then the rest of the air is pushed towards the HEPA filter and is filtered there. So this is a two-stage filter, and not just the HEPA filter is not sufficient for using the lead or cleaning the lead. So here I'm going to show you the video of uh, cleaning the lead. Bear with us for this advertisement to go away. Yes. So you can see several areas were defined by these squares, and the beam is quite small, maybe about 3-4 centimeters small size, 3-4 centimeters in size, and it's cleaning, and the pipe is removing the lead particles. This is a lead paint. You can also increase the size of the beam. It doesn't have to be only 2-3 centimeters. It could be 20 centimeters. So here you can see the size of the beam has increased, and it is taking care of a bigger area. So these are all adjusted from the either the iPad or the encoder. You can adjust these parameters for the laser cleaner. Okay, next is the Canada Aviation Museum. So we took our 100-watt laser there, and these engine parts were all rusty. There was soot and oil on them. So let me show you a video of how this was cleaned.
So you're going in and out to try to get the focal point?
Yeah, so when you get onto a stopping area too, sometimes.
So this is one, and you also have this other video. The soot and rust are being cleaned.
So right now you'd be burning carbon, lead, petroleum.
Okay.
I'm sorry, soot and oil. So this could be carbon, lead.
You'd have to be like a joint venture between
Okay, and this is the last case study, Coro scan, non-destructive testing. So this uses the capacitive 2D imaging and impedance spectroscopy. So if there is a point where there is rust, it could detect it, and if it is underneath the paint layers, it could tell where the rust is, and this uses this capacitive method to identify the rust. So in the shipyard trials, when we did in Irving, we used this Coro scan, which is quite useful for identifying the location of the rust. So here we get to some general applications. Again, we haven't done these, but they can be done with laser cleaner. So on the right side, you have cleaning in the food industry, where you can clean these barbecue plates using near IR lasers. These particles, they stick strongly to the surface. Near IR radiation is highly absorbing by the metals, and also by they are highly absorbing by the food particles that they could remove from the surface of the metals. And on the left side, you have the bacterial removal. Here's this paper, as I've given as a reference, used several different types of lasers, CO2 lasers, YAG lasers, in different harmonics. You have the UV and near IR, and they compared the performance, and it turned out that both YAG laser at 1.06 and CO2 lasers are very effective in removing bacteria from the surfaces because they form sticky biofilms on the surfaces, and it's hard to remove them with detergents. It's easier to remove it with the laser cleaner than with the detergents. It's also more effective. So with this, we come to the conclusion of our talk. So the takeaways from this talk is we looked at the fact that laser cleaning is more environmentally friendly, reduces damage to substrate, has a great selectivity because you can tune the parameters. It doesn't use secondary medium, reduces health hazards, is less noisy, more economical as compared to other methods. And when you take into account all costs, and we looked at some of the uh, impact of laser parameters and material properties, and what are the optimum values that you can use for better cleaning. Uh, we talked about accessories that we designed to mitigate the disadvantages. We compared the CO2 laser with near IR laser, and we mentioned that all the CO2 lasers are inherently safe, but they're bulky and they're not compatible to fiber optics, and for this reason, it is better to use a near IR and tune the parameters than use a CO2. Uh, and then we showed that for shipping industry, laser cleaning could be a very good replacement so that it doesn't damage the environment and pollute the environment. And also the case of robotic laser cleaning in a radioactive environment where we removed F18 radioactive isotope from several different metal surfaces. The result of this research was also presented as a paper and an oral presentation in Waste Management 2023 conference in Phoenix, Arizona in February 2023. So with this, I thank you very much for listening to the talk. And if there are any questions, please feel free to ask. Or you can type if you like. You can also type in the chat. So I'm just going to write my email here. If you think of any questions later and you want us to, look at your particular case that you want to clean, or project that you have, you can email me, and I would make sure that some of our experts will get in touch with you to examine, what it takes, or provide you a quote. So, is there any question?
Well, I have a question.
Yes, please.
I'm curious about the pricing on the portable 100 watt, but also whether or not any of the products are available to lease or rent.
Yes, 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 definitely the products are available for lease and rent. Lease, it's actually lease, not rent. And as far as the pricing is concerned, usually it's about $100,000 per 100 watt. Okay, so if you're looking at 100 watt, 100,000, 200 watt, 200,000, 300 watt, 300,000, 500 watt, 500,000. That's how it works. But if you like, I can ask our CEO to send you the lease rates. If you send me an email, I have your email, and then I'll ask him uh, to send.
Okay, thank you.
You're welcome. And then Andre is asking a question. Sorry, let me answer this question first. Andre G is asking, does it heat up the material? Yeah, there is heat. Of course, there is heat. Let me show you one slide that I have here. Yeah, this I did not talk about this particular graph, but this was removing rust from stainless steel. So the y-axis is the temperature in Kelvin, and this is the fluence. Different colors represents the fluence. So the melting point of stainless steel is about 1800 Kelvin. As long as the fluence was less than 3 joules per centimeter square, the temperatures were under control and fine under the melting point of stainless steel. But as soon as they increased the fluence to above 3 joules per centimeter square, then there was a sharp rise in temperature, and melting of substrate happened. So there is some heating, but it is controllable. You can control it using the parameters of laser cleaner, and we have certain recipes to make sure that it would not damage the substrate. Any other question? Someone else had a question. Hello? Is there anyone else? I hope I answered your question satisfactory, Andre. Uh, if there is any other question, please feel free to ask. All right, seems that there's no more questions. So once again, I thank you for your attention and attending the webinar. If you have any suggestions, please, we'll send you a feedback form. Let us know what you want us to talk about more in the next webinar. And as I said, we'll send you the recording and also the YouTube videos of the webinar. All right, so thank you very much and have a safe afternoon. Have a good afternoon and stay safe. Thank you. Bye.